Well, hello. Welcome to a little corner of the internet called Marshable Math. This is Mr. Marsh. Today we're going to do a review of basic exponential and logarithmic functions. So get yourself a piece of paper and a pencil or the worksheet, and let's begin. Okay, so you're familiar with some basic things like this. Y is equal to x squared, which gives us a quadratic kind of a graph. But what if we make the variable the exponent? Your basic exponential function looks like this. Y is equal to a times some base raised to the x. Now notice that the variable is the exponent now, not the base. Let's talk about some terms. A is the constant. B is the base. And x then is the exponent. And so now some properties of these things. The constant is always going to be the original value. The y value being the final value. The a value is what you get when x is equal to 0. So when x is equal to 0 at the beginning, the a is your original value. The base then is going to be the multiplier. You're going to be multiplying the original value by some factor, some multiple. And you're going to be doing it repeatedly because that's what exponentiation is. It's repeated multiplication. And so the exponent tells you how many multipliers you're going to use. So for example, if I had y is equal to 2 times 3 to the x, and I'm going to let x is equal to 2 now. This gives me y is equal to 2 times 3 squared. Or what that means is it's 2 times 3 times 3. I have two 3's, so whatever that is, and that's going to be equal to then 18. Or what if I had something where x then would be equal to 5? It would look like this. Y is equal to 2 times 3 to the 5th. So that's y is equal to 2 times 3 times 3 times 3 times 3 times 3. So I'm tripling it 5 times. So just keep track with your a and your b and your x. The b is always the multiplier. The a is always the original amount. Now, second principle that we have is this. If I have two things equal to each other that have the same base but different exponents, if b to the x is equal to b to the y, the bases must be the same, then I can stop and do a new equation. I can say, therefore, x itself must be equal to y. But this is only true if the bases are greater than 0 and the base is not equal to 1. That's one of the restrictions that's on this thing up here too. The base has to be greater than 0 and it can't be 1, because if you repeatedly multiply something by 1, it doesn't do anything for you. Alright, so now, third principle. Let's get into logarithms. A logarithm is just kind of a backwards way of dealing with exponents. A logarithm asks, what is the exponent? So the answer to a logarithm is going to be an exponent. So recall a long time ago you learned that 3 squared was equal to 9. We have to now have names for all of these things. So the 3 is easy, that's the base. The 2 is called the exponent. And 9 then is the power. And I'll admit, sometimes there's some sloppy vocabulary going on. Sometimes the 2 itself is called the power, but no, the answer to the exponent is called the power. So you would say that 9 is the second power of 3, but the subject of the sentence is 9. 9 is the power. If we were to rewrite that as a logarithm, we would say log base 3 of 9 is equal to 2. Notice that my base is dropped below the line, so you get to drop the base. But the 9 and the 2 are all written on the same spacing of the line as normal. Do not raise the 9 up as an exponent. It's not a superscript. The only change to the scripting format here is the 3 has to be dropped below. So to write this out in words, we would get log of the base, or log, the base goes there, power is what is inside the parentheses there. That's what you're taking the logarithm of, and that equals the exponent. So now, if you were to say this out loud, log base 3 of 9 is 2. Well, let me write it out for you here. You would say log base 3 of 9 is 2. That's how you would say it in words. If I were to rewrite the exponential thing now in words, it looks like this. You would have your base written on the line, and then your exponent would be a superscript, and then that's equal to the power. Okay, so the answer to a logarithm is the exponent. The logarithm is asking what is the exponent on the base that gives you the power. And sometimes the thing that's inside the parentheses here is called an argument. And that's true for things other than logs, like trigonometric functions and so forth. So if you hear me talk about what's the argument of a logarithm, I mean what I'm taking the logarithm of. All right, so now it must also be true then, I think we're on point number 4, that if I have a log base b of x and it's equal to another logarithm, also the same base, of y, the only way that this is true is if I have a new equation of x equal to y. But there's some restrictions here too. Your argument can't be negative. You cannot take the negative, you can't take the logarithm of a negative number or of 0. So some restrictions here, I would say that logarithm of a negative number and the logarithm of 0 are both not allowed. So whatever your power is, it's got to be a positive number. It can't be 0. And the reason for that is because your base is always 0. If I do an example here from, say, 3 squared is equal to 9, 3 to what exponent, because that's what a logarithm is asking, is equal to a negative 9. Now your base has to be positive. So what exponent do I put on 3 here that changes the sign from a positive number to a negative number? And hopefully you can think this through and say, well, this does not exist. If there's no exponent that makes a positive 3, a negative 9, well, somebody's going to say 3 to the negative 2. No, that's equal to 1 over 3 squared, because a negative exponent means the base is on the wrong side of the fraction bar. So move it. Or somebody would say, oh, that's 3 to the 1/2 or something like that. No, a 1/2 is a root. This would be the square root of, don't have to write the 2, I'm just pointing it out, 3 to the 1st. So neither one of these give you an answer of negative 9. So the exponent does not exist. Therefore, if I said log base 3 of negative 9 is equal to something, you would say, hey, that can't be done. No such number. And if you're an Elvis fan, that would be then return to sender. But that's a side point. Okay, so now let's look at some review problems here. Let's do some questions on this worksheet right here. So the directions say graph each function and state the domain and the range. So let me come in now and do number 2. So I'm going to zoom in. And I'm just going to plot some reasonable, some thoughtful x and y values. So x on the left, y on the right. So the simplest one here is just going to be 0. So what's the y value when I let x equal 0? So that's going to be 2 times 1/2 to the 0. Well, 2 to the 0 is 1, and so 2 times 1 is just going to be 2, right? So you see how this gives us y is equal to a times b to the x, that when the input is 0, we just get a as the result. We just got 2. So 0, 2, that would be this point right here on the graph. Now let me do an x value of 1. So what is 2 times 1/2 to the first? 2 to the 1/2, or I'm sorry, 1/2 to the 1 is going to be 1/2 times 2 that's already there. That's going to give me 1. So if it's 1, 1, that's going to be that point right here. Let me go ahead and do 2. If I did 2, what would it be? So that's going to be 2 times 1/2 squared. 1/2 squared, isn't that 1/4 times 2? This gives me a value of 1/2 for the y value, so about right there. Oh, by the way, I have a nice mantle clock in the room that I'm doing the lesson in, so welcome to 3 o'clock in the afternoon, though I'm not doing this at 3 in the morning. Although I could if I really wanted to. All right, so then let's do -1 for the x. So what does that give us? That gives us, I'll do the math down here, that gives us 2 times 1/2 to the -1. Well, 1/2 to the -1, the negative exponent means the base is on the wrong side of the fraction bar, so flip it over. So 2 times 2, that would give us 4. So go back 1 and then up 1, 2, 3, 4, that location here. Oops. There we go. And then if I do, say, -2, this is going to give us 2 times 1/2 to the -2. That's going to be 2 times 2 squared to the +2. Flip it over. So that's going to be 4 times 2, which is 8. So back 2 and then up 1, 2, 3, 4, 5, 6, 7, 8. And that's this right here. Now, can you see what the shape of the graph is going to look like? Comes down, smooth curve, never touches that x-axis. And if you remember, we have a boundary line here that is going to be y is equal to 0 is the equation for that line, and that is an asymptote. Asymptote is a boundary line that the graph does not cross at its ends. It might cross in the middle. So when you do pre-calc at some point, you'll probably do some asymptotes that you do cross it in the middle, but it's at the ends. Okay, so now this we can see is a decay graph, decay function, and that's because our b value is less than 1. It's always got to be greater than 0, but our b in this case is equal to 1/2. So what we're basically doing is we're repeatedly multiplying 2 by 1/2. So we're taking half of 2, which is 1, gives us this point. Half of that again gives us a half, which is that point, and further on down. So we're repeatedly multiplying 2 by 1/2. We're taking a half and a half and a half and a half and a half repeatedly. Okay, I will let you, if you're doing the worksheet, I will let you do the remainder of those. Now let's do solving this equation right here. So first thing I notice is I've got my equal sign right here, and I've got something on the left and something on the right. I see that they're exponents. It's 4 to the x plus 35, and it's 64 raised to the x minus 3. Now, if these were the same bases, I could equate the exponents, because if the bases are equal and the things are equal, then the exponents must be equal, but the bases aren't equal. So my question is, can I rewrite 4 as something involving 64, or can I rewrite 64 as something involving 4, or maybe some other base? And the best way to do that is to make the larger one something involving the smaller one. So let me rewrite 64. So this becomes 4, stays the same, 4 raised to the x plus 35. And that equals to something, something, x minus 3. How do I write 64 as a power of 4? Well, if you've got that table memorized, or you can check it on your calculator, we should realize that 4 raised to the third is equal to 64. So I haven't square rooted anything. I'm not raising both sides to the third power, because that would not only change the 4, that would also change the 64. I'm not doing any kind of algebra transformation. I'm not doing to one side of the equation the same thing that I'm doing to the other side. I'm just rewriting 64 as an exponent of 4. And so then what do we do with exponents when we raise one to another one? We multiply them. So this now becomes x plus 35. That doesn't change. This is now going to be 4 raised to the, multiply the 3 into that group right there. That becomes 3x minus 9. Careful with that there. I'm not taking 3 cubed and calling it 27, or 3 plus 3 and calling it 6. I'm multiplying the 3 into this 3 and calling it 9. All right, so now are my bases the same? Yes. Stop. New equation, x plus 35 is equal to 3x minus 9. Okay, now I solve this one. I'm going to move the x to the right side. So minus x here, minus x there. And I'm going to move the 9 to the left. So plus 9 here and plus 9 there. And these cancel, and these cancel. 35 plus 9, 44, and that equals 2x. And now divide this side by 2, divide that side by 2. This cancels, I get x is equal to 22. Now, just double check. Are there any restrictions on putting 22 in for x on that? Nope. And so I try this. Go ahead and plug it in and see if it works. See if 4 raised to the 22 plus 35 is actually equal to 64 raised to the 22 minus 3. I bet you $1 you will get the same answer. Okay, now let's move on to number 3 here. Write an exponential function for the graph that passes through the given points. Okay, I'm going to change color to blue. An exponential function is what we started off with in the review, that y is equal to a times the base raised to some exponent. So we've got to find out what a and b are. Well, the long way of doing it would be to start with this one and actually plug this in for x and y. So I would say y is equal to a times b raised to the x, and then I'm replacing x and y. Y is 5, and that has to equal a times b to the 0. I'm replacing the 0 in for x and the 5 in for y. But what is b to the 0? That would just be 1. So I get 5 is equal to a times 1. So, but there's my a. Remember I told you that a was the original value? So if your input is 0 to start off with, the y value right there is going to be your a value. All right, so I figured out what a is now, and now I need to find out what b is. So I do the same process over, but this time I use my value for a that I found. Y is equal to 5 times b to the x, and now I use the other point, this one right here. So 3,125 is equal to 5 times b to the 4. All right, so now I got to solve this one for b. I'm going to be taking the 4th root at some point to get rid of the exponent, but I need to divide both sides by 5 to begin with. So I'm going to divide the right-hand side by 5, divide the left-hand side by 5. Those cancel. And let's see here, I've got my calculator in hand. 3,125 divided by 5 is equal to 625. And that has to be equal to b to the 4th. Good. So now, how do I undo raising something to the 4th? I would do the 4th root. The 4th root of this. Or, this will cancel. Or you could say it's 625 to the 1/4 exponent. Same thing. So my b then is going to be, I'm going to do it as an exponent because I'm on a smaller calculator. So 625 raised to the 1 divided by 4. Make sure it's all in the exponent. And I get b is equal to 5. Okay, good. Well, but they're both 5. Okay, so what that means now is when I put them all together, I'm going to write an exponential function now. So I get y is equal to 5 times 5 to the x. There's my final answer for my function. Okay, if you're up for a challenge, try number 4. But I'm going to move on now. Number 5, let's just take a look at this one real quick. At time t, there are this many bacteria of type A and this many bacteria of type B, organisms in a sample. When will the number of each type be equal? So what am I setting equal to each other here? To set this one up, I'm setting 216 raised to the t plus 18, set that equal to 36 raised to the 2t plus 8, and I got to solve that for t. So what would your strategy be there? Well, probably the same thing that we did right here on 7.2.1. If we can get bases that are the same, we can then equate the exponents. So I'll let you think about how to get the same base out of 216 and 36 by just rewriting them. Okay, so write each equation in exponential form. What does that mean? It's not doing any math other than just reinterpreting it. So if I said something like what we did before, 3 squared is equal to 9, to write that in logarithm form will be log base 3 of 9 is 2. So they're asking, if you're given the logarithm, can you go back and rewrite it as an exponent? And the hint I have for you on that one is to do what I call the log loop, which says you start with your base, because you always start with the base, and go around to the exponent. 3 squared is equal to 9. Okay, so number 3 here, rewrite in exponent form. Okay, so the power is 1 over 81. Start with the base. The base is 3 raised to the negative 4, 1 over 81. So 3 to the negative 4 is equal to 1 over 81. That's all you have to do on that one. Just rewrite it. It's just interpretation. Can you write it as an exponent when it's given to you as a log? And on this one, can you write it in logarithmic form if you're given an exponent? Okay, so I'll deal with this one right here. All right, so log, what's the base? 3 of, the power goes next, 81, equals 4. Remember, logarithm asks, what's the exponent? And is 4 my exponent? Yes, it is. So done with that one. All right, so now evaluate each expression. Evaluate means to find the final simplified value, the numerical value. So let's take a look now at number 15. Logarithm asks, what's the exponent? It's asking, what's the exponent on 2 that somehow gives me 1/16? So what is the exponent there? Well, I can tell you right away that it's going to involve a negative because 2 is a whole number, but 1/16 isn't. So it's going to be flipped upside down. So the thing that flips the base is going to be a negative. And then 2 to the what is equal to 16. So 2 to the something is equal to 16. Well, I know that 2 squared is 4. 2 cubed is 8. And then times 2 again, 2 to the 4th, that's equal to 16. So it would be then negative 4. So the final value of log base 2 of 1/16 is negative 4. Okay, so moving on now. How do you solve these equations? There's 2 different kinds here that you're going to find to begin with. One of them looks like this. So I see my equal sign here. I've only got one x right there, but it is set up as a logarithm. But I only see one logarithm. So my strategy on that is to get the logarithm package all isolated, which it already is. It's not logarithm of 3 of something and then plus something else, or 5 times the logarithm of that. It's just log base 3 of this thing, 4x minus 17 is equal to 5. Well, the question that a logarithm asks is, what's the exponent? So all I'm going to do is do the log loop. I'm going to take 3, raise it to the 5th, and that has to equal the thing that's inside the parentheses, 4x minus 17. And so now it's solved just like a simple algebra one. I can find out what 3 to the 5th is. 3 to the 5th, 243. That's equal to 4x minus 17. So I solve this now by adding 17 to both sides. Add 17. And I get 260 is equal to 4x. Divide that by 4, divide that by 4, and I get x is equal to 65. Now, are there any restrictions on what x can be? If I plug 65 back into the original equation, does it give me a negative thing? It's 4 times 65 minus 17. Is that a negative number? The answer is no, so I'm good with this one. There's your answer. Okay. Now, let's try the next one down below. Let me give a little space here so your mind can see that. All right, so I see my equal sign right here, but oh no, I've got my variable there and my variable there. But look, I got two logarithms, but their bases are the same. So remember this principle. Log base b of x is equal to log base b of y. If they're two logarithms equal to each other and the bases are the same, we can then say, okay, then x must equal y. So that's what I'm going to do. All I'm going to do is I'm going to take the arguments and set them equal to each other. So x squared minus 4 then has to be equal to 3x. And notice what I did. I always put parentheses around my argument, even if the printed material isn't there, because I need to see the argument of the logarithm as a group. Okay, so now this is just quadratic. How do I solve a quadratic? I set the right side equal to 0, so x squared minus 3x minus 4 is equal to 0. Did that by subtracting 3 from both sides. Do I have factors of 4 that when I subtract them give me the number 3? I sure do. So it's going to be an x and a 4 and an x and a 1 equals 0. What do my signs have to be? How do I get a negative 3? Well, it has to be a negative 4 there and a positive 1 right there. So now I use the zero product theorem and set each factor equal to 0, because when two or more factors are multiplied and the product is 0, one or more of the factors must be equal to 0. And so then I get x is equal to 4, and I get x is equal to negative 1. Okay, but now I got to check them. If I plug 4 in to either one of these, to the x squared minus 4, or into this one over here, do I get a 0 or do I get a negative answer? So if I plug it into x squared minus 4, that's going to be 16 minus 4. That's a positive 1. That's fine. And if I plug it into 3x, that's also a positive 1. That's fine. So x is equal to 4 is a solution. Now, what if I take the negative 1 in and plug it into this argument and to that argument? Well, if I do negative 1 squared minus 4, that's going to be 1 minus 4. That's equal to negative 3. I can't have a logarithm of a negative 3. And if you see, it also makes this one negative 2. It makes it negative 3. So this one is out. This is called an extraneous solution. Extraneous solution is one that you get when you do the proper algebra, but does not actually solve the original equation, and so you have to discard it. And I think that is all for today. Well, I hope you're having a good day. Hope you learned something, and look forward to seeing you next time. Bye-bye.